We start. This is the department of the normal physiology, and this material is devoted to the physiology of the heart, the electrocardiogram, and the phases of the cardiac cycle. And I was able to present to you all this material in this very complicated picture. First of all, this is the structure of the heart, and you see this is the conductive system of the heart. The heart includes two types of the myocardium fibers. This is the typical myocardium fibers and atypical myocardium fibers. Typical myocardium fibers may be excited and conducts this excitation. At the same time, they may be contracted. But the atypical myocardium fibers, they have lost the ability to be contracted, and they may only be excited and conduct this excitation from one cell to the other cell. Conduction system consists of the sinoatrial node at the right atrium, the atrioventricular node, the bundle of His with two branches, and the Purkinje fibers. The heart has the property of automaticity. What means automaticity? This is the spontaneous contraction of the heart. The ability of the automaticity has the heart, there are some neurons in the brain, and the smooth muscle cells. The sympathetic and the parasympathetic nervous system might change the heartbeat rate, the strength of the heart contraction, and the same may do the hormones. But the reason of the heart contraction is located in the sinoatrial node, all the other cells, typical and atypical myocardium cells, may be spontaneously produce the action potential, but it happens at the heart diseases. Normally, at the healthy body, only the cells in the sinoatrial node produce the action potentials. The sinoatrial node consists of approximately 100 cells. In each cell, the action potential starts. What is this? This is the curve which explains the membrane potential in the inner surface of the membrane of one cell in the sinoatrial node. This have no the resting membrane potential. The maximum negative electric charge at the inner surface of these cells is equal each cell, but the cells approximately 100. The maximum negative electric charge is equal minus 70 millivolts. This is the timeline in milliseconds. And in these cells, in the membrane, spontaneously, the special channels are open, the channels to the calcium ions, and in second power, and sodium ions. And that start to permeate in this cell, and the negative electric charge little by little decreases. This is no process, is no slow diastolic depolarization. Slow because this is the rapid depolarization. This is the slow depolarization. Depolarization, this is the decrease of polarization. The decreases happens from the minus 60 to minus 40 millivolts. When the critical level of depolarization, this line reaches the critical level of depolarization, all the sodium pores are open, and depolarization, the rapid depolarization starts. After this will be the repolarization to the level minus 60 millivolts. It depends on the outflow of the potassium ions. The sodium ions stops in but the potassium ions outflow, like in all other excitable cells. But the peculiarity of this action potential, that this action potential has no the spike form. This is the sinusoid form. After this, immediately starts the slow diastolic depolarization again, and will be the next action potential. The action potentials or excitation stands to conduct along the both atria, right atria and left atria, with the rate of excitation conduction 1 meter per second. Then it reaches the atrioventricular node and starts to conduct in the septum of the heart with the rate 3 meters per second. And in the Purkinje fibers and in the myocardium cells of the ventricles, 1 meters per second. This is no very small difference between 1 and 3 meters per second. But in the atrioventricular node, the rate of excitation conduction is decreased, and it is only 5 centimeters per second. This is known atrioventricular delay. Delay happens because there are no close contacts in the atrioventricular node. Between all the cells in the heart, typical and atypical myocardium cells, happens the close contacts, which they are known nexus. This is the electrical synapses. The excitation conducts without mediator from one cell to the adjacent cell. But there are no nexus in the atrioventricular node. The distance between these cells is more, and the excitation conducts can jump from one cell to the adjacent cell. How many these cells? 100, approximately the same. But it needs more time, and the rate of excitation conduction is decreased. Why it needs to the heart walk? During this period, both atria are contracted, and the blood pumps out from the atria into the ventricles. And this is the time, this time of the moving of the blood depends on this atrioventricular delay. Without this atrioventricular delay, the 4 chambers of the heart will contracted at the same time. They would be contracted at the same time, and the blood from the atria can't flow in the ventricles. But atrioventricular delay regulate the movement of the blood from the atria into the ventricles. The main characteristic of the excitation conduction, this is the ECG, electrocardiogram. At the ECG, we see some waves, P wave, Q, R, S, T, and segments between these waves, P, Q, S, T, and TP, because after this will be the next cardiac cycle and next combination of these waves. The appearance of the emergence of this wave depends on the excitation conduction in the, first of all, both atria. The excitation conducts. This is the part of the excited part of the atria. It conducts, at this part appears the local current. This local current results in the electromagnetic field. This electromagnetic field conducts in all parts of the body around the heart, in the head, in the arms, in the foot, and principally we may register the ECG if we take the 2 metallic electrode, large electrode, and put between the 2 places of the heart. But usually we put the electrodes in the medicine in certain places, on the wrist of the heart, on the legs and register these waves on the ECG. That's why, what is the reason of, it is askable at the exam, what is the reason of the waves on the ECG? First of all, this is the reason, this is excitation conduction in the heart. The excitation conduction depends on the local currents between the rest part and excited part, like between the nodes on Ranvier in the myelinated nerves. Around this electric current appears the electromagnetic field, and special devices, electrocardiographs, register this difference of the electric charge of this electromagnetic field between the two certain parts of the body, between the two arms, or left arm and left leg. Then all the atria are excited, and excitation conducts in the atrioventricular node, atrioventricular delay. This is the time. We don't register the waves because the electromagnetic field is very small. But this excitation can't produce the electromagnetic field. Electromagnetic field appears only the excitation starts, or it is finished, or it conducts from one place of the heart to the other place of the heart. Then the next, the excitation disappears in the both atria, little by little, here and here, but then it conducts along the bundle of His and excited the papillary muscles. This is the very important muscles, and it attach to the septum. And the direction of excitation conduction is reversely. That's why the Q wave show us the excitation conduction in the papillary muscles. It is negative. Then the excitation conducts from along of the typical and atypical myocardium fibers to the apex of the heart, and we register the R wave. Usually at the exam, it is asked why the R wave is more than the P wave. Because it depends, the amplitude of the waves depends on the amount of the excited fibers. The more fibers, the more amplitude of the wave on the ECG. Both ventricles are thicker than the thin both atria. That's why the amplitude is more. Then the amplitude moves from the apex of the heart to the direction of the basement of the heart to the atria at the side walls. And this is the reverse direction of excitation conduction, and we register the S wave. The S wave is negative. It depends on the excitation conduction at the side, at the lateral walls of the ventricles. Then all the ventricles are excited. This is the period when in the atria we have no the excitation, but all excitation presence in the both ventricle, and we register ST segment, the straight line. It is askable why this is the straight. Does the excitation is present? Yes, it present, but it prolongs, it doesn't move, it doesn't appear, it doesn't disappear, and it doesn't conduct. That's why there are no electromagnetic field. This no electromagnetic field because the excitation doesn't move in the both atria. This no waves because the excitation is present, it continues, but doesn't produce the electromagnetic field. And then starts the disappearance of the excitation. The excitation disappears from the apex to the basement of the heart and starts the T wave. After this, all the heart have the rest, and this is the resting membrane potentials on the all heart myocardium fibers, and that's why we have the waves. This is the TP segment. Then after this, the next excitation automatically starts in the sinoatrial node and results in the excitation of the atria and starts the new P wave. This is about the excitation. This part is devoted to the cardiac cycle. If the medium average frequency of the heartbeat is equal 75 contractions or heartbeats per minute, it may be more, less, but this is the average rate of heart contractions. And this is 75 per minute. But 1 minute consists of the 60 seconds. And we divided 60 seconds to 75 and have not 0.8 of a seconds, or in milliseconds, this is the 800 milliseconds. The work of the heart consists of the systole and the diastole. Systole and the diastole. What is the systole? This is the contraction of the heart and pumping out the blood from the heart in the arteries. Diastole, this is the relaxation of the heart and filling with blood from the veins. Atrial systole consists of systole, 100 milliseconds and 70 milliseconds. This is the duration of the diastole. In the ventricles, the systole starts after the systole of the both atria. The duration 330 milliseconds. And after this is the diastole, and during the systole of the atria, this is the diastole in the ventricles. Summation 100 and 370 will give us a result 470. If we plus this value and this value, we have the duration of the heart cycle, 800 milliseconds. But this is the main two stages of the heart contraction. But we have a lot of the smaller stages of the heart contraction. First of all, this is the first. This is the atrial systole. This atrial systole. This is the more complicated picture of structure of the heart, like when we discussed about the excitation conduction. This is the right atrium. This is the left atrium. This is the right ventricle and left ventricle. And the excitation start conducts from the sinoatrial node, and both atria start to contract. This arrows shows this contraction, these arrows. And first of all, the orifice of the veins are closed, and the blood pressure increases from in the right atrium to the 5 millimeters of mercury, and in the left atrium to 10 millimeters of mercury. The atrioventricular valves, these lines shows the position of the atrioventricular valves. It consists of the flaps. This is the tricuspid valve, and this is the mitral valve. Both of them are open, and the blood flows during the period of the atrioventricular delay from the contracted atria to the right ventricle and to the left ventricle. The pressure becomes 5 and 10 millimeters of mercury. Then after this starts the contraction, the systole of the both ventricles. It consists of the, first of all, second and third. This is first, and this is second and third. Asynchronous contraction and isometric contraction. What is the asynchronous contraction? This is the no synchronous contraction. Not all the two chambers of the ventricle start to contract at the same time. First of all, start to contract only the typical myocardium fibers at the end of the Purkinje fibers. Purkinje fibers here, here, and the length of them, typical myocardial standard, start to decrease, but the adjacent myocardium fibers are stretched out, and in common, all the volume doesn't change. This is this very small period. But during this period, at this picture, I present to you this at this picture, I present to you this situation. This is the contraction of this. This is contraction. This is the stretching out between these 2 points. And but the diastole happens in the atria, and the blood pressure decreases from 5 to 0 and from 10 to 1 to 2 millimeters of mercury. And the blood wants to move in the reverse direction, but the flaps of the atrioventricular valves start to move to the orifice of the atrioventricular orifice, here and here. But after this, immediately starts isometric contraction or isovolumetric contraction. This is the same. This is the very rapid contraction. These arrows shows this, and very rapid. All the typical myocardium fibers start to contract. The blood pressure increases from 10 to 80 millimeters of mercury in the left ventricle, and from 5 to 15 millimeters of mercury in the right atrium. And the valves are closed immediately, atrioventricular valves, tricuspid valve and mitral valve. They are closed, and they start to vibrate and produce the first sound. We can hear with the help of the auscultation, or if we put our ear on the thorax wall, we can hear tuk tuk, tuk tuk, tuk tuk. This is the first tuk. This is the first sound. This is the result of the closure of the atrioventricular valves. Then these waves, the sound waves, conducts in the blood, in the lungs, in the thorax wall, and we can hear these sounds. This is only the first sound. This is the presence of the closure of the atrioventricular valves. Blood pressure increases, and after this, volume doesn't change because all valves are closed. This sticks. This is the semilunar valves. This is the aorta. This is the lungs arteries, and these valves are closed. During the isometric contraction, all the valves, both valves, 1, 2, 3, 4, they are closed. And that's why the pressure increases without change of the volume. Isovolumetric or isometric, no change of the length of the ventricle, no change of its volume. After this starts the 4th and 5th periods, the phases of the systole of the ventricles, rapid and slow blood injection. The blood outflows, pumps out from the ventricles in the large arteries, in the aorta, and then flows to the large blood socket and to the lungs arteries, and flows in the small blood socket. The blood pressure continues to increase. The wall of the ventricles contracts. You see these arrows. the volume decreases, and the blood pressure reaches 120 millimeters of mercury in the aorta and 30 millimeters of mercury in the lungs arteries. And how many blood flows out from the heart during the systole of the ventricles. I put to you these values. This is the end diastolic volume. How many blood before the systole of the heart? How many during that period, after the contraction of the both atria? The volume is equal 125 milliliters. You doesn't need to multiply it by 2 or divide it by 2, because in each chamber, in the right ventricle, 125 milliliters, and in the left, the same. Then the blood flows out during the systole with the pressure, high pressure, and the stroke volume, it is no stroke volume. How many? 65 milliliters. Not all the blood pumps out from the ventricles. A little bit more than a half of the volume. If we make the subtraction, we have 122 minus 65, we have the 60 milliliters. This is the end systolic volume. That's why after the contraction or systole of the ventricles, the amount, the volume of the in each chamber in the right and left is equal 60 milliliters. This is the average values. If the person, the individual is very high and have the high wave, the volume will be more. If this is the small girl, the volume will be less. And a very important parameter, this is the cardiac output. We multiply the stroke volume, 65 milliliters, to heartbeat rate. Heartbeat rate, 75 heartbeats per minute. And we have approximately 4,900 milliliters per minute. Approximately, it is equal 5 liters per minute. This is the cardiac output. Every minute, heart pumps out 5 liters per minute at rest. But at the physical work, this cardiac output will be increased. That's why this is the very hard work of the heart. And the heart needs every time a lot of the energy from the carbohydrates, and it needs the oxygen to oxidize this. After the contraction starts the diastole. This is the diastole. It includes the 4 stages: protodiastole, isometric relaxation, and filling with blood the chambers of the ventricles. At the beginning of the diastole, the blood moves in the large blood socket and in the small blood socket. But these atrioventricular valves are open, and the blood wants to move reversely in this chamber, and it is closed. This is the cross section at the level of the aortic valve. It consists of the 3 flaps, or these flaps are like the pockets on the white gown. They are closed, first, second, and third. When the blood pressure open these valves, the pockets moves to the side wall of the aorta, and the blood outflows. Then they are closed again and produce they are vibrated and produce the second sound. And we hear tuk tuk, tuk tuk. This is the second tuk. This is the second tuk. Second sound on the phonocardiogram. I'm very happy that I can very rapid to present to you this material, and one more.